Sure. So, our next speaker is Andrew Gelman.
Okay. Yeah, so it's a pleasure to speak here with all these young researchers who are doing very sophisticated methods. And here are just some things that are going to come up. I wanted to start with an often useful approach in mathematics, which is that if you can't solve a problem, embed it in a larger problem. And where it's very appropriate to talk about that in the Isaac Newton Institute, where mathematicians are famously lazy. As the saying goes, Isaac Newton would literally invent a new branch of mathematics to avoid going to therapy. Like, not quite, but he literally invented calculus just to solve some physics problem, right? And it's, we know as mathematicians or as applied mathematicians, the beauty of brute force, right? Like, calculus is brute force, not like Archimedes had all these really clever ways of figuring out the volumes of solids. Calculus, just brute force is the way to go if we possibly can. And when I think about in statistics, so often we do this. So often we embed. And one example is actually Bayesian inference itself. Here's a problem that's kind of hard to solve. Maybe I don't have a lot of data. And so I am going to solve the larger problem, the class of problems where the parameters come from some prior distribution. That's a harder problem to solve. Yet, by thinking of it that way, I can do a little bit better. A lot of examples of hierarchical modeling. I do a survey in the United States, and I want to estimate public opinion. I get lots of people. I want to estimate public opinion by state, and I might have a little state like Wyoming where not very many people live, and out of the 12 people in my sample from Wyoming, maybe all 12 support the Republican candidate. I don't think 100% of people in Wyoming support the Republican candidate. There's no amount of weighting. There's nothing I can do with those 12 yes responses to get an average other than 12, but I can embed it in a larger problem and say, I'm going to estimate what happens in all 50 states. Right? So if I can do that, well, if I fit a hierarchical model, then I would partially pool the estimates of Wyoming to the national average, which is, of course, terrible. Because Wyoming is not really an average state. So instead, I would want to use a group level, state level predictor like Republican vote share in the previous state, and then I can do that. I can get a better estimate. So I've embedded in a harder problem, in a larger problem. And of course, mathematics, when you can't solve a problem in prime numbers, they solve it in the space of ideals. There's Andrew Wiles over there, a big embedder. A lot of the talks I've seen at this conference have been this way. People talk about generalized Bayesian inference. So Bayesian inference is great. Let's solve a harder problem and do more. So I appreciate everything that you all are doing. I think you're really following in that tradition. Statistics is the science of defaults. We have a motto in statistics, never be clever. And I say this kind of as a textbook writer and a software developer, that I can't, I want methods that people can use. And again, a lot of examples of this we see when we learn probability. There's the famous Monty Hall problem. Sounds so tricky, but if you draw the tree, it's very easy to draw. We don't like to leave anything any mysteries. We want things to be as brute force as possible. Statistics is hard, and I want to give you a couple examples just to demonstrate the challenges of kind of naive thinking. So these are real examples that came up. One was many years ago. It was it's a problem where someone had, it was a biology experiment, and they had data in, they were measuring the growth of, I think it was bacterial cultures. And they had 4 treatments, A, B, C, and D. Each one was applied to 5 dishes, and each dish had 6 bacterial cultures in it. 6 for B, 6 for C, etc. I'm drawing them in this weird way, or 5 dishes for each one. I'm drawing it in this weird way to emphasize there's no two-way structure here. It's just a pure nested structure. So, okay. The person involved, he had 2 possible analyses he was thinking of doing. So the cultures are in dishes just to save money, to save researcher effort because they're not supposed to interact. So there are 2 models you could do. The first thing is you can take the average of all, I'll call it Y bar 30, the average of the 30 measurements for each one. So for C and D. The other thing you can do is I can first take the average within each one and then average the averages. So I'll say like Y bar bar, and it's an average of 5 things. Well, these are the same averages, you might realize, so there's no difference. But what's the standard error? Well, this is different, right? This, you get the standard deviation divided by square root of 30, this divided by square root of 5. So big difference, which should you do? So they were going back and forth. On one hand, they have no reason to think that cultures interact within a dish. On the other hand, like, what if they do, right? And so this thing, well, this is going to give you much, it seems like it will give you a much more precise estimate, but it's making a pretty strong assumption. This one seems more safe. On the other hand, they had strong belief, strong knowledge that these things wouldn't interact. So the question is, which to do? And there's an answer, actually. So I'm going to just put this aside for a minute. The other example I wanted to give is the chickens example. This one, it's a little background about this. Back in the 80s, 70s and 80s, some epidemiologists found a connection between exposure to low-frequency magnetic fields and childhood leukemia. And they were finding a risk ratio of like 1.5 or 2. And on the other hand, these are case control studies. There's always iffiness about it. It wasn't clear how to interpret this, whether to believe it or not. Now, to jump to the end, people have looked into it, and they're pretty sure that low-frequency electromagnetic fields don't actually cause kids to get leukemia. It's just that it's not people who are living near low-frequency electromagnetic fields have other issues, other risks. But we didn't know that back in the 80s. And then the question was, if a low-frequency electromagnetic field, like from these lights or whatever, or power lines, is giving you cancer, how would you do it? It's too low. There's no X-rays coming out. It's too low energy to be ionizing your cells. It's not even microwaves. It can't even cook your cells. So, but if it had an effect, how could it have an effect? How could a 60 hertz or 50 hertz hum affect you? Well, it turns out that your brain signals, brain waves are roughly 60 hertz. So the theory was that they could interact and interfere with brain signaling and stop your body from fighting cancer. Not impossible. During the 80s, some biologists did some experiments where they took some chickens, they killed a chicken, break the chicken brain in 2 parts. One part gets the treatment, which is exposure to the low-frequency electromagnetic field, a specified frequency. The other one doesn't get it, gets the control. And then they averaged over a bunch of chickens and did a series of experiments at 38 different frequencies, from like 15 hertz, 30 hertz, 45 hertz, so forth, and then saw what patterns they might find. Okay, well, they wanted to be careful, just like these people, they wanted to be careful. So they did, for each, they duplicated each experiment with a sham experiment, a sham experiment. So the regular experiment, one half gets the exposure, the other doesn't. The other experiment, just like that, same frequency, same everything, except the machine's turned off, so nothing's going on. So, sham. Okay.
Andrew?
Yes.
Suggesting waves in the brain of a dead chicken?
Oh, they measured calcium efflux. Sorry. Good. No waves. Yes, calcium channels are like where the communication goes. So they actually measured the flow of calcium outside and I will defer to others to say whether that's relevant. But this is like the way science often goes, right? We have there's some model, some hypothesis. You try to find something you can measure that's connected, trying to find a result that's stable. I don't want to use the term statistically significant, so I won't. But I'll say a result that's stable and replicable, and then from there, you use that as a kind of stylized fact that you move forward for. So it's fine as science. Okay, so here's the question. What should you do? You can use two estimators. One is I can take as a treatment effect, I can just take the simple difference. Well, I'll just say, y bar treatment minus y bar control. Or I can do y bar treatment minus y bar control for the exposed experiment minus y bar treatment minus y bar control for the sham. So it's kind of like this. There's two choices. This is like you're living on the edge because you're not using the sham. This one, you're correcting for the sham, so this would correct for potential biases. On the other hand, if there's no sham effect, you're just adding noise here. So it wouldn't be a good idea. So then the question is which to do. So just spend 30 seconds with your neighbor telling me which you would do here and which you would do there. Talk to each other just to commit a little bit to the idea. Here, you can talk with him. And you can talk with those guys behind you. Just 30 seconds is all I ask.
Yeah, it's
Okay, so here, so I'll tell you the answers. The answer to the first one is you should do the average of the 5, because, well, okay, if there is correlation inside the dishes, obviously you do the 5. If there's no correlation, then I was kind of tricky when I describe the problem, because yes, it's an average of 5 things you divide by square root of 5, but you're averaging 5 averages. So if there's no dish effect, then the averages are themselves have standard deviations that are divided by square root of 6 implicitly. So in fact, the second one gives you everything you would get from the first one for free. Now, strictly speaking, what would I do? I would fit a multi-level model. I would estimate the extra variance. It gives you a little more statistical efficiency because it is true that the bottom one you only have 5 degrees of freedom to estimate the variance. So, but you get most of the way just from the second one. So that would suggest the meta principle that when in doubt, be careful. This one, the right answer is this. And you can see that it depends on the data. But if you look at the data, which the average data are available, there's actually no evidence of any sham effect. The sham, there's just nothing going on. It's complete. The data from the sham are completely just consistent with no sham effect, which makes sense because they're dead chickens. I don't know what kind of placebo effect they were hoping for. But the point is, yeah, like it seems safe, right? So the principle of well, go with the safe approach. Okay, this will not always work. And and there is a tendency, in the paper they did this, and there's a tendency to say, well, let's do this just in case, let's be safe. But somewhere along the line, they're trying to make decisions and understanding about the effects of magnetic fields and so forth. Interestingly, in the paper about this, they wrote, well, we still have a lot of uncertainty. Various things are statistically significant, but we're not sure what's happening. Really, we should do more experiments. They never did more experiments because they were busy, right? Well, actually, if you do this, this is equivalent to doubling your sample size. If you didn't even take the sham measurements, that would be equivalent to quadrupling your sample size or doubling. So, well, maybe you need some sham measurements. So this is an experimental design question. They had 38 experiments. With only one experiment, you couldn't tell what to do. But with 38, you could figure that out. So if you know you're going to do 38, you should probably start by doing some sham, and then at some point you should stop doing it. Embedding into a harder problem, right? Solving 38 is harder than solving 1, and yet you can do better. You can double your efficiency. So that's pretty great. I want to give you yet another example, then I'm going to talk more generally. This was a study of stenting. So this stenting is something you can do when you have a heart problem. It can allow the blood to flow and unblock your artery, and I don't know the details. But it's a thing that people do. Sometimes it's done prophylactically, so people don't absolutely need it, but they're having some difficulty with their breathing, and they will do stenting. An experiment was done to estimate the effect of stents. And the result of the experiment was that the p-value was 0.2. And so that was reported in the newspaper on the front page, I believe, saying that stenting has no effect. It was a typical science story in that the news article said, this was a big shock. Everybody thought it was going to be effective. It's still effective if you really need it, but in this other side. It's that, so the big news. Everyone thought it was so effective, and it's not, right? Oh, but also they quoted people as saying, yeah, well, you know, we always wondered about it. That's why we did the experiment in the first place, right? Which is true. They wouldn't do an experiment on something that they knew worked, right? So it's kind of awkward. I looked at the paper, and it was interesting because they compare. They have the pre-treatment group and they have the stenting group, the treatment and the control group, and then they have the pre-treatment measurement and the post-treatment measurement. And it was randomized. There's no statistical significantly difference between the pre and post-treatment. The outcome is the gain score. In this case, it was treadmill time. So how much longer people could walk on the treadmill. These were patients who could walk for an average about 500 seconds on the treadmill. So it's the increase in treadmill time. The estimated, taking this difference in differences gave them an estimate, a certain estimate. It was 16 seconds plus or minus 13 seconds, something like that, 0.2 p-value. So I looked at the paper, and it had the averages for the pre-test, and you can actually see that although the difference in pre-test scores was not statistically significant, it was different between the two groups. And you can adjust for that. Taking gain score is not the statistically efficient thing to do. The statistically efficient thing to do is regress the post-treatment on the pre-treatment. Doing the gain score is like running a regression, constraining the coefficient to be 1. It's like doing this. It's very intuitive to people. It seems perfect because it adjusts for all biases or whatever, but it's actually wrong. So very easy, the data were right there. They had just enough summary, not the raw data, they had just enough summary statistics that I could recalculate it. The estimate went up, and the standard error went down. Okay, now at this point, I had dollar signs in my eyes. Not dollar signs exactly, but I was excited because the p-value was already 0.2, right? So if by doing the correct analysis, it suddenly made the result, real, this would be a big deal. Like, look, this simple statistical idea that everybody knows it's in textbooks, and they did it wrong. It was high profile, big budget, top journal, newspaper. Okay, so the new estimate went up from 16 to 21 seconds in treadmill time, and the standard error went down very slightly from 12.7 to 12.6. The resulting p-value is 0.09. Boy, was I bummed, right? It would be a much better story if it was p equals 0.04, because then I'm telling you, that would have rocked their world. However, as often is the case, we learn more from our disappointments than our successes, right? So the question was, what do you say about something like this? So I think, and I realized that my way of thinking was wrong. Because I had two ways of thinking about this. One is to say that, well, p-value is 0.09. Like, it could happen, right? It's consistent with an O. Another thing I could do is I could say, well, I have a 95% confidence interval, let's say, and my 95% confidence interval goes from like -5 to like from -5 seconds to 40 seconds or something like that. So it looks like the effect could be positive, but it could be zero, I'm not sure. What do you do with that, right? I could just say, another thing is I can just say, well, I don't know, like I'm a Bayesian, like here's the range, okay? What are people supposed to do with it? Not clear. So I was talking with a colleague about this, and he pointed out that, oh, and there was kind of a larger problem, which is that our default Bayesian analysis with a flat prior has this very weird property. So if you have an estimate that's one standard error away from zero, which is kind of potentially pure noise, right? If an estimate's one standard error away from zero, if you have a flat prior in the effect size, your posterior probability is 84% that it's positive. So like if you assume flat priors, it's a very weird thing because data that are completely consistent with noise would allow you to bet 5-to-1 odds, which doesn't seem right. And yet, I mean, that's what Bayes says. Well, of course, that would be correct if the true effect were really coming from a distribution with very large variance. Because if your true effect size came from something with a distribution of very large variance, and you saw something that was just one standard error away from zero, it really is 84% chance that it's positive. On the other hand, if the truth came from a distribution with such a wide, then it would be very unlikely you'd ever see something that's one standard error away from zero. It's actually evidence against the prior. Like you shouldn't be seeing, if the world had really, really broad priors, you shouldn't be seeing things that are close to zero at all. So it's the very fact that you're seeing that is telling you the problem. In this case, we had a prior though, because my colleague created a prior distribution of effect sizes based on the Cochrane database, which are these registered medical trials. And we used a mixture model, but it's roughly, let's say, Cauchy 0-1. It's not too far from that. That's a prior not on effect size, but on signal to noise ratio. So our estimate is that the true signal to noise ratios of high quality medical trials are roughly like that. So actually, most of them are of signal to noise ratios that are less than 1, but some of them are larger. If you do that, we can pump that through our inference and get a posterior. And then I went back to the original paper. So the question was how they designed the study. And they said, well, they powered the study to be effective, have high enough power if the true effect on treadmill time was 30 seconds. So 30 seconds of treadmill time. Well, that's not that much if the average is 500 seconds, but it actually is a lot in the sense that nobody claimed that this was going to be the one treatment that would like make all your problems go away, right? If your treadmill time is 500 seconds and it can be increased by 30 seconds on average by a treatment, that's actually pretty good. An average treatment effect of 30 means it's going to be 60 for some people, maybe 0 for others. That's a real effect. So we can take our posterior based on this Cochrane database. We can get a posterior, not a posterior 95% interval. I don't really want that. I don't like 95% intervals, even though my books are full of them. I feel bad about that. I don't know. The endpoint of the 95% interval is itself very noisy. I don't know what to do with it. It feels to me like an attempt to get certainty where no certainty exists. I can make a statement, though, from what's my posterior probability that the effect is positive in this case? 93%. That's just what it comes out to. What's the posterior probability the effect is between 0 and 30 seconds? 80%. What's the probability of the posterior probability the effect is more than 30% on average in treadmill time? 13%. So this study, I think that the right way to report this study is not, oh, damn it, shoot, it's not statistically significant, but rather, here's the posterior probabilities. It looks like it's positive. It looks like there's a small positive effect. There could be a tiny negative effect. The data are consistent with a large positive effect. But that's worth it. That could have been it wouldn't have been on page 1 anymore. It would have been on page 15 of the newspaper, right? Study estimates a small positive effect. But this is all mathematically trivial, but this is really interesting to me. It changed my way of thinking. Like now I feel like I know how to answer these questions, how to summarize this. And it's none of the answers I knew about. It's not the flat prior Bayes. It's not the 95% confidence interval. It's not the 95% posterior interval. It's not the probability that's positive. It's like, this was really something. Now, at this point, you might say, well, is there a moral hazard here? Because if a researcher knows that I'm going to do this analysis, and see, one thing you get is even if, and by the way, it would have been almost the same thing if the p-value had been 0.2 or 0.04. Like this, it's not this threshold. It's okay. But what if you knew? So one thing we learned is when you do a randomized experiment, you get a positive estimate. The effect probably is positive, right? Like unless you have prior information otherwise. But not only that, like it's pretty strong. If you have an estimate that's 1 standard error away from 0 from the Cochrane database, then you actually have not 5 to 1, but 3 to 1 odds that you got the sign right. So that actually means, I really believe this. I actually believe that if people are doing medical studies and they're not cheating, people cheat. That's another story, right? Like they have, you know, you want your result to be believable, so HC generalizable, so you do a multi-center trial and you contract out, and then you have these companies that do clinical trials and they want to keep getting hired and getting successes. So sometimes I've heard that sometimes they can be pretty good at when someone's in the control group and they're recovering, they manage to like and they miss an appointment, they kick them out of the study. And if someone's in the treatment group and they're recovering and they don't respond, then it's like, hey, you forgot an appointment, come back. You know? So there's a lot of cheating. Okay, cheating aside, if you do a study, in your 1 standard error away from 0, I'm actually willing to bet at 3 to 1 odds, at least if your study was randomly drawn from the Cochrane database or something comparable. That creates a moral hazard. Anybody can do any study, and then they're likely to get 1 standard error away from 0. Like that happens, then they'll get 3 to 1 odds. Like publication ka-ching solves all science problems. Well, of course, then I wouldn't use that prior, right? So I'm assuming like that would have to be embedded in the analysis that you're doing. You would not use that prior from the Cochrane database, for example, if you were studying social psychology studies. Yes?
Did you question if they were measuring the right variable?
Well, they had many outcome measures. I'll take their word for it that treadmill time was a reasonable outcome. So I think it made sense. I'm not an expert, but I did collaborate with experts on this. Okay, so big picture. In the last 20 years and more, there have been huge successes and embarrassing failures of science. And obviously successes, all sorts of vaccines and bombs and all sorts of wonderful things that science can do. And even more humble world of developing little drugs or A/B testing in industry. People learn a lot. There's also been a lot of prominent science failures associated with the term replication crisis, having to do with interpreting statistically significant results. How can statistical ideas help here? I think that a key principle is the principle of generalization, that as I said, rather than talking about statistical significance, I'd rather say, does this result generalize? So I'm not going to argue with someone about whether their result on their data set was statistically significant. I'm going to argue about whether what they think is going to happen in the future. Right? This again relates to the embedding problem, embedding into a harder problem. So you do an A/B test in January on some set of customers. You're interested in how this treatment is going to be effective on a set of potential customers in future years or future months. It's a generalization problem. There's a funny paradox in a lot of statistical examples where people add information and it makes their confidence, their uncertainty intervals wider. I do a study and I estimate the effect of this treatment. Okay, that's fine. And then I said, well, some other people did studies and they all did studies, and now I do a meta-analysis and I say, well, I don't know what's going on. Well, I think the problem in some sense was not with the later meta-analysis, but with the first study that people did, because they were implicitly assuming it would generalize. So I would say even if you only do one experiment in one place, you still should add those variance components when making predictions or making statements about the future. Now, why is statistics so hard here? A few years ago, Rob Tibshirani wrote something he called the bet on sparsity principle. And it was a kind of Pascal's wager. And his argument was that statistics is fundamentally like impossible. Like making inference about things you haven't seen can only be done with strong assumptions. So he said, you assume the world is sparse, and assuming the world is sparse, you can learn from it. And if the world isn't sparse, you can't learn anything anyway, so let's assume that's bet on sparsity. And this works in a lot of cases. For example, you have a photo, an image has tons of information, and you try to identify who are the people in the image. That's obviously a much lower dimensional problem. There's a very sparse underlying structure that you care about. So it solves a lot of machine learning problems. And I remember a few years ago, I was at this conference at the university where an astronomer came up and he talked about how he had like zillions of data points and he was trying to understand the structure of the universe. And then someone came up who's doing remote sensing, and she had even more data, and she's just trying to determine like two things, like classify things on the ground in terms of what crops they were or whatever. And then I got up and said, well, as a political scientist, they have like 1 million data points and two parameters. I have 1 million questions I'm asking and 2 data points. Wow. And we can't easily get more data. I mean, we can't say, oh, we want to estimate the effects of political things, so let's get some data on let's create some more recessions to see the effect of the recession, or let's create some more wars. Well, I guess some of our politicians are doing their best to give us more data in this way, but that's not really a general thing that can be done. So we really have local sparsity, and that characterizes the problems that I work on. And that's what makes, that's our kind of motivation for using prior information and for expanding into larger problems. Now I'll get to workflow in a moment, and I want to first say that the history of Bayesian statistics and statistics in general, I think, is bringing things inside the tent. Kind of like science itself, like all sorts of phenomena in science which seem incomprehensible, like thunderstorms or whatever, like now we have models for. I wrote this, that in statistics, there's been centuries of turning ideas which might have been called philosophy or good practice into models and mathematics. And I give you some examples. One example is exploratory data analysis, which is even now often presented as a kind of be a good person. Look at your graph, look at your data. Exploratory data analysis is posterior predicted checking. It's what you're doing when you do EDA is you make a graph, which is a kind of test statistic, and you compare it to the graphs that you would have seen if your model were true. When we do posterior predictive checking, we actually make those graphs. But if you do a residual plot, you're looking at the residual plot of the data, you're comparing it to the residual plots you would have seen had the model been correct. It's just that in that case, sometimes your graph is designed so cleverly, remember, never be clever, but this graph was designed so cleverly that its reference distribution barely depends on the underlying model. That is, I don't need to simulate potential. If I do a QQ plot, you can make your quantile plot of data. You need to simulate some QQ plots in your process to see how far they could be off the line. But with a residual plot, you don't need to simulate anything because you kind of know what a residual plot's supposed to look like if the model is true. But in general, exploratory data analysis is you look at the data to learn the unexpected. So what does that mean? You're learning the unexpected. That's what you didn't expect. It's relative to the expected. So it's a form of model check. Indeed, one good idea, if you're ever looking at a graph, is to say, what am I trying to learn from this graph? If I can learn something unexpected, it's not a bad idea to write down what you're expecting before you make the graph. And so it's a form of model check. So now exploratory data analysis is not something outside of formal statistics. It's actually part of it. It's predictive checking. Another example is exchangeability. So you've heard about exchangeability, right? Like we have, we got 38 experiments, and we're trying to, might fit a model to estimate these effects. Well, are they exchangeable? Let me use the other example of our polling. We partially pool the inferences from the 50 states in order to get estimates, state-level opinions from national polls. Are the 50 states exchangeable? Well, they're really not, I don't know if I should say that they're exchangeable. I don't want to fit a hierarchical model because I don't know if the groups are really exchangeable. What does it mean? It seems very philosophical. Are you a real Bayesian? Are you really, what do you think? How do you test whether something's exchangeable? It's an assumption. You can't test the assumptions. That's why they're called assumptions. It's horrible. Okay. Well, there's things you can do. So for example, people we have an example of the 8 schools. So it's experiments estimating the effects of a treatment on 8 different schools in New Jersey. This is some classic experiment that my PhD advisor did many years ago before he knew me. And you can do a hierarchical model. I don't know if those 8 schools are exchangeable. Well, what does that mean? Well, maybe some of them are public schools and some are private schools, and the effects are different in the public schools and the private schools. You can do that. We actually know which are public and private schools. You can put a predictor in your model, and then your question about public and private schools ends up being a question about the coefficient of that predictor. You can have a prior on it. So what we've done is we've kind of changed the philosophical question into a modeling question or a math question. Because I could say, for example, well, I think there's some public schools and some private schools, and they're different, but I don't know which is which. But I could fit that too. That's just a mixture model, right? I can express my uncertainty as a model and do that. Another example, since I mentioned Wyoming is I won't get into that. I go to Wyoming. But so you're not American, so it'll be a little complicated. So it has statistical content. Okay, so we have many examples. There are examples like model selection and averaging, problems where we expand Bayesian formalism. Another example is estimating the parameters of the prior distribution. So way back when, they used to have this thing saying, well, Bayes needs a prior, and you don't know the prior, but you can estimate the prior from the data. We call that empirical Bayes. It's a new kind of inference. But then in the 60s, Box and Chiao and others recognized that you can frame that as a hierarchical problem. So it's actually, Bayesian includes this in general, because you can just say that the hyperparameter is unknown, and we could do inference for it. So you no longer had to have a philosophy, you just had to have a model, and it all ends up turning on what's your prior distribution for this unknown group level variance parameter. And it turns out in a lot of problems that prior matters if you don't have a lot of groups. So in moving away from a philosophical question of what form of inference I should use toward a question about how large could this variance be, is something potentially empirically addressable. So workflow. Workflow is an increasingly popular word, and in statistics, here's how I think about it. We have, at one extreme, we have an example. We do something new. This is what we do. Like in computer science, what you do is you have a method, you try on a benchmark problem. That's great. That's not what we do in statistics. In statistics, we have a problem we couldn't otherwise solve, and we solve it. That's an example. But what do you do with the example? How do people follow? Remember, we're the science of defaults. It's hard to know what to do. So the next thing we would do is create a case study. And the case study, that's like the example, but you state what you did. You state all the steps. Then ultimately what we'd like to have is an actual algorithm, or a theorem even, or an algorithm, or a method. Right? Well, somewhere in between there's something called workflow. So workflow is something that's more stylized and formalized than a case study, but it's not quite an algorithm or a method. And that's what I've been interested in that recently. And that's kind of what I wanted to talk to you about. And so somehow this talk has that form. I'm giving you a bunch of examples in some sort of case studies, which is kind of showing the need for some workflow. And when we talk about statistical workflow, there's two aspects of it. The first are the steps, if fitting a model isn't a problem, there's what we call statistical workflow. So just suppose that you're working on problems that are simple enough, or you have algorithms good enough that you can actually fit the model you want to fit in Bayesian sense. I can simulate data, I can fit models, I can get posterior simulations, I can do that. There's still a lot of steps of workflow. And you don't always see that, right? Because in the textbook, it's like, here's the goddamn model, right? And then you you fit it. But actually, there's a lot of steps to get to that, which I'll briefly talk about. Sometimes it's framed as the entire Bayesian workflow is what's your prior, which is kind of nuts. I mean, because I don't know what the prior should be. It's so subjective. I don't know where people's logistic regressions and all were coming from. We say this, people will swallow the camel that is the likelihood and then struggle on the gnat that is the prior. I think that we need to think about the models we construct and how we put them together and what they apply. The other part of workflow is what if fitting is a problem? And we spent lots of time on this, right? And that's what a lot of the talks here are about. It's hard to fit, so what can we do here? And this fits in, to me, with the idea of Bayesian inference or statistics as a history of things being formalized. Because I think that the idea of, to me, I would say the key idea that I want to leave you with is the concept of the sequence of models. So there's, where did I have, there was a saying of Winston Churchill, because we were eating at Churchill College, and it was that at times of war, truth is so precious, it must be attended by a bodyguard of lies. And I think that our models we fit are so important that they need to be accompanied with other models. So usually the way this is framed is we have a model selection problem, or we need to adjust for model selection, or maybe we have a model averaging problem, something like that. Maybe even a model expansion problem. I want to say, even if you tell me, here's the model you know that you want to fit. You know it. Maybe it's right, or maybe whether or not it's right, it's the model you're going to fit. I would argue you should be fitting other models. So, for example, if we're doing pharmacology and we're fitting a 4-compartment model, I want to see the 1-compartment model, the 2-compartment model, the 3-compartment model, the 4-compartment model, and the 5-compartment model. Now, why do I want to see that? Well, first, I want to understand what I got out of adding these compartments. Did I get anything? Was it even necessary? And I want to understand the model based on what came before. Then I want the 5-compartment model just to convince myself I didn't need it. And I think that's always the case. So what does that tell us about computation? Well, I think this moves us away. Hamiltonian Monte Carlo, Markov chain Monte Carlo, all these things, these came from physics problems. The paradigmatic physics problem is I have a problem and it's well-defined, and I want to estimate something to like 5 significant figures, and I'm going to crunch my computer for a few weeks and get the answer. But the paradigmatic statistics problem is, first, I don't need anything to five statistical significance, 5 figures. In fact, I'd be happy with 10 independent simulations. If I could have that, that would be enough. I do not need my endpoint of my 95% interval to be computed with 2 digits of accuracy. That's nothing to do with real science problems. I think I need to do more than 10 iterations when I run Stan, even if it's running well, because I need to run it long enough so that I know I've run it long enough so I've finished well. But I only need like 10 independent iterations. I don't need lots of them. So, but also, I'm not really interested in running something overnight, over 3 weeks. I don't even want to wait 5 minutes, to be honest, because I'm going to be fitting a lot of models. Partly because I'm going to be experimenting, and the models I fit are probably wrong. But even if I knew which I want to fit, I want to fit these other ones. And I just think that's not in the statements of the problems that we usually frame. Now, when it comes to constructing the models, again, I think it gives us, we're under a little less pressure if we're fitting more than one model. And we can always do predictive model averaging, we can always do stacking, but I think this, like, trying to come up with just the right thing is not so good. Now, also, the other reason we fit multiple models is just computational. When we do approximate computation, which we're often doing, that can be framed as an approximate model. Right? So if I have some complicated thing and I approximate it by a mixture of normals or whatever it is, that corresponds to some implicit model I'm fitting. And when we fit multiple models, it's not just that this little model helps you understand the big model. Another example would be causal inference. So I think we see this a lot, like in applied economics. Here's the causal effect. Here's the estimated causal effect. We adjusted for all these things in epidemiology. I always want to see, what's the raw difference between the two groups? What happens after you adjust for age and sex and blah, 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 blah? What is that estimate doing? I want to understand that. Right? So part of it's purely understanding. I think it's scientific mispractice, the way we present our results, by just giving the final answer of that. But the other thing is, for computation, it's like warm start, right? This earlier model is the starting point for this model, the starting point for this model. That's super important because that's often how we tell that our models have problems, is that the results don't make sense. I wanted to have a t-shirt made that said, initialization is a part of the algorithm. Because it is. You see all these papers, like, how did you initialize? Words so bad, like in Stan, I was using the default inits. We had a problem, it was very interesting. So I had this idea, just for fun, testing out Stan, because we have differential equation models, a planetary motion example. So we create a simulation, you got a sun here, and then you've got a planet, and it's moving around the sun in an ellipse, but instead of giving the formula for the ellipse over time, you just have the differential. It starts at a certain initial velocity, and then you have the laws of motion. Here we are at the Isaac Newton Institute. We're using his laws of motion. And then you get the position over time, like this. And then it's measured with error. We simulate some error, just like the astronomers in Isaac Newton's day. Now I want to estimate where everything is. We decided we make it easy, and we'll actually even let you know, like the star position we'll assume is known. Super easy problem. Differential equation, program it up in Stan. We run 4 chains. 3 of the chains are fine. They give estimates, which are basically right, like this. They're doing just fine. The 4th is like really bad. You see, like, no mixing. R hat is like 50 or whatever. Like, nothing's mixing well. You can look at the target, the log density function. The log density function, I think, was like, it was like 300. It was like, I think it was like 3 times 10 to the minus 5 lower in this other chain. I mean, when I say this is the log density was this much lower, which means the density was a factor of e to the minus 3 times. Okay, so it was, you could throw that chain out. That was okay. But usually when we have problems like this, say, well, what's the problem with this? It had to do with, was doing this. It was, instead of saying, yeah, it went like this, like it went 1.5 times around, which was kind of a terrible fit, but it was a local optimum. And so the funny thing about this is no prior is going to solve this computational problem. It's a multimodal posterior, but one of the modes is like, has essentially 0 mass. So you can't, you could throw that mode away. But I'm saying this only because you can also realize it's a bad problem. It doesn't fit the data in some way. Or you could use better initializations. But this is a problem where no amount of brute force of the computation would solve it. You have to, because there is this mode. Often when we have a minor mode, you can get rid of it with the prior, but no prior would be strong enough to get rid of the local mode of this, because locally it turns out to be the best fit. So yeah, initialization being important. Also, even things like sensitivity analysis, like how does the model change, how does the inference change if you take out a data point? That can be thought of as a change of model, right? So removing a data point would be like saying that this data point comes from another situation, another place. So I think the model, thinking of computational methods as actually being new models as well as being approximations to an existing model, I think is a very fruitful way of thinking about it. I can't get into all those, but let me tell you about the fail-fast principle and the folk theorem of statistical computing. So the fail-fast principle is that we are often going to be doing things that are wrong, like this, or fitting models that are bad. We want to learn that quickly. Now, the way our algorithms often work is that when the model fits, they go really fast. And when the model doesn't fit, they go really slow. They get stuck. And that means, like, our usual way of operating is to say, we're trying to come up with methods where when the problem is, when you have it specified well, you get the right answer. We have to have methods where when the problem is specified poorly, you quickly blow up. You quickly give a problem. And our defaults, we're not always doing that. It's a real problem. This was a big workflow issue that we would fit models, and that when the model wasn't good, they took longer. And it's a little bit like, I don't know, have any of you ever submitted a paper to a journal or a conference proceeding, maybe? Have you ever done this? So do you know there's this system called reviewing where, okay, well, how does that work? Well, the best papers, they get their 3 reviews and they get published. The worst papers, they get rejected, then they get sent to a new place and you might get 15 reviews before it's published. Then the most influential papers, they still don't get any more reviews. They're just out there. So almost all the review effort is being spent on papers that nobody reads. And disproportionately on papers that get rejected multiple times, but also even most accepted papers nobody reads, right? And more efficient would be a post-publication review process where just about everything gets published, maybe it gets 1 review or a half a review, then when things start getting cited, then they get reviewed, right? All the effort's going the wrong place. That's what happens with us, with computing. Often, our biggest efforts, the slowest things, now some of that's unavoidable, because some of it's not computation time, it's your brain time figuring out what went wrong. We didn't immediately realize this was the problem. It took us a while, even though it was obvious in retrospect. So you need to, so we have to be aware of that, which changes our workflow. Now the folk theorem of statistical computing is that when you have a computation problem, you often have a modeling problem. So that has a lot of meanings. One is that computation can be a form of model check. So for example, I'm fitting a model to some data and it's really slow. I'm running Stan or whatever you're running, your own computation. It's super slow, it feels sort of bad. Okay, well you know what you can do? You can simulate fake, I don't know if you've ever done this, simulate fake data from the model and then try to recover the parameters because you know the parameters, because you simulate from the model. Often it turns out that even though your online computation is super slow, when you try simulating fake data on the model you're fitting, it'll converge really fast. The lack of convergence is itself a function of, right? The speed of convergence, if you run like HMC and you compute R hat, ultimately R hat's a function of your data, right? Conditionally your model, it's just, you put the data in. It's an actual test statistic, and you can actually test it, do a posterior predictive check by simulating fake data from the model, and often you'll find that things converge better if the data actually came from the model. Now, you don't always have to do that formally, so even informally, we often notice this. And just, we should be aware of this because in our workflow, what's the traditional thing that people do when something is slow to converge? You run it longer. Well, that takes less thought. But really, once something's slow to converge, you should already be worried. You should think about expanding the model, all the tricks that you would do, like pinning parameters, simplifying. Sometimes it helps to simplify a model, but sometimes it helps to make it more general. So, for example, I have time for one more example, or not? Just stop?
You have to trade off with questions.
Okay, well, I'll stop except just to say that I had an example that came up recently where it was like hard to fit, and then I set up a hierarchical model, and it was easier to fit. You know, so it made it easier. Other times I had a problem that was hard to fit, and I set a certain variance parameter to 0, and then it fit easier. So again, we don't always know. So in conclusion, we have a need for generalization. That's all of statistics, right? Machine learning. We have data here, and we want to learn about something over there. Or even if we want to learn about what happened here, we want to learn about other conditions, counterfactuals. We want to generalize. The need for generalization induces sparsity in our data. Our data are sparse. They're not dense. They're sparse for the questions we want to ask. And if the data are not sparse, then we'll ask narrower and narrower questions until they reach sparsity. That's the natural, the absorbing state of data analysis is sparsity. And that motivates us to fit models. And that leads us to need workflow, because fitting models is difficult, partly because it's hard to fit things because of the geometry and the math, and partly because our models are always wrong. That's it.
So what's the example?
Oh, it's not that interesting. I was fitting logistic student exam scores. So what I do for each exam question, I can regress the student's score in the exam with their total score on the entire test, and that way you can look at the discrimination and see, like you do, like if it's a positive slope, that's good. Students who did better on other questions did well in this question. If you have a negative slope, it's kind of weird. I had a negative slope, and it turned out that I had actually graded the exam wrong, and so I discovered that. But it turns out it's hard to fit logistic regression on just a few data from a few students, but if you have a lot of questions, the hierarchical model stabilizes it, it regularizes. Yes?
Thanks. So I found your comment really interesting to say initialization is part of the algorithm, and yet it seems sometimes that the initialization question is a little bit treated perhaps in a less principled way than the question of how do we design MCMC algorithms. So I'm curious, did you identify in your experience good ways that are robust?
I don't have a great answer. My general principle is to frame it as a series of models. So I would frame the initialization as an estimate from a previous model. But sometimes people initialize by drawing from the prior, which could be fine, but I wouldn't say that's a general principle. I would say then the previous model is just the prior, like that's a previous model. You can't always draw from the prior like that. But that's how I do it. Yes?
When do you stop and say the model is good enough?
Oh, well, you know, I try to summarize what we got, and then, I think that depends on your applied question, and often, like you want to understand like what made the model work. And I don't think at some point you have to stop, but you want to be transparent about it. 21 seconds, yeah.
Where does interpretability come in?
What?
Like interpretability?
Oh, yeah, well, I think that the sequence of models that we call the topology of models. So if I fit a series of models, what's important is not just that there's a sequence of models that are getting more complicated, but that they talk to each other. So I have this idea, I don't know how to formalize it, but like think of graphical model. Okay, so I have a graphical model. It's sitting here like it's a little, with lines connecting the nodes and edges. Now I can do operations on that graphical model. Like for example, posterior predictive check is an operation on a graphical model where I introduce new nodes and edges corresponding to replicated data. Prior predictive check is another kind of extension of the model where I introduce new nodes for newly simulated parameter values in new data. A simulated simulated replicated data from the model. I'm actually drawing new parameters, hyperparameters, and then checking. Each of these things is a kind of topological structure, one could say. It's an extension of the graphical model. Now, if I have model 1 and model 2, model 3, typically I'll try to either interpret parameters in the model, like how does the coefficient of theta change as I add more predictors? Well, there's no reason why the coefficient of theta is a different model, but I have an additional assumption. Part of the topology is that theta is connected. I might have other parameters that, like here I fit a GP and here I fit a spline. Well, the parameters in the GP and the parameters in the spline are not connected to each other in any simple way. However, they have predictive quantity, maybe their predictions are somehow connected. So there'd be this, I think more work would have to go into it. Like interpretability, again, the idea of bringing things inside the tent, that interpretability is not just like being a good person. Interpretability, statements, questions of interpretability are kind of topological questions about the network of models that you're fitting. Yes.
Thank you so much for your talk. I have a comment more than a question. We had a number of discussions about the reviewing process throughout statistics and machine learning during the program. I will not go into the detail. I just wanted to add that there is a concept, the American Mathematical Society has these mathematical reviews, which is doing a bit what you suggest.
Post-publication
Post-publication reviews.
Good.
So if you're interested in mathematical reviews, I think they are always happy to have more people looking into them and maybe contributing to the reviews.
Yeah, I think we had a proposal that all journals should have a policy that every time a paper hits 100 citations that they get external reviews. Not to accept or reject it, it's already been accepted, but just to assess its importance and look for mistakes. The current system is just terrible.
Okay, thank you so much.